Okay, so everybody should see the recording button there in the top left-hand side of the screen. So that indicates we're recording. And then, Brandon, I gave you co-host, so I think you can share your screen.
Yeah, I can.
Okay, cool. So the floor is yours.
All right, great. Thank you, Dr. Tran. Before anything, just Dr. Tran, if you could just alert me when 30 minutes pass, because
Okay.
I'm assuming I can get through these slides in 30 minutes, so I can go into other advanced mechanical material topics that people have requested me to do. So yeah, I'm gonna just try to speed through it, or I'm not gonna try to speed through it too fast, but I'm going to basically go over the main overview of what I'm doing today. And yeah, let's just get started then. So hi guys, my name is Brandon. I am your grad TA for this class. Let me go ahead and share my screen real quick. Okay, share. Okay, great. So yeah, I'm great. I'm your grad TA for this term. And I was in charge of 3 lectures. Unfortunately, on 1 lecture, I got unnecessarily sick. So a video about that lecture subject will be posted soon. But in the meantime, so today, what we're basically going to go over is the design considerations for your 3D bioprint. Dr. Charles, did we already tell them that they're doing 3D bioprinter? Okay, okay. So we're going to go through their design considerations for the 3D bioprinter. And oh boy, it is really hard to get into the slides. Hold on, because the UI for the UI for Zoom is in the way. There we go. Okay, and start from again.
Yeah, and we'll I just had a question come through chat about whether the slides will be posted. So after we're done, yeah, we'll put them up on Canvas.
Yes. Okay. So this slide, this presentation, I was asked to do this sort of as a introduction to design of 3D printing, although we haven't really done something like this prior. And I'm trying to keep chat open right now while I'm doing this. Well, it's kind of hard to see while doing it at the same time. So really what I'm going to do in these design considerations, I'm just going to overview last year's designs and critique them essentially as your introduction to how to make these 3D printers given a maybe concept of budget or limited resources, knowledge of different utilities or tools or mechanisms you can use to apply to your design. This is sort of supposed to give you some idea going forth, and then a couple touches on some engineering analysis, but just a touch. Really, it's supposed to more introduce you to the fact that we're engineers and we can analyze pretty much anything as long as we make the right assumptions, make the right calls, and basically don't upset our customer. So with that being said, so let's just get right ahead and start. So the overview of this presentation is going to generally first talk about, I'm just going to summarize 3D bioprinters in general. I'm not going to go into too much detail. All the sources I got for bioprinter subjects, we've already posted it on Canvas, so you can look up the papers for those. So just a general brief overview, maybe some tidbits of what to consider when you design it if the customer required it. I wasn't there when the customer talked to you guys, so you guys will know that better than I do. Some key metrics, what I found to be primal when I was looking through prior reports, and what I see as a hierarchy focus in lit, not too focused, but sort of touched upon in an expletive manner. Then crucial modules. This is just something I hashed in. This is more opinionative based. This is what I consider the crucial things you would probably need for your 3D bioprinter, but every bioprinter is going to have a different subject, different module, and different way. Every group is going to tackle this differently. So my crucial modules don't necessarily reflect what you guys are going to probably do. I'm just going to reflect on what I've seen in the papers and in the past reports. Finally, I'm going to show you some examples of past reports, pros and cons of each. Then we're going to have a brief look into different analysis archetypes. I say archetypes because what this basically means is I'm going to just touch upon how some engineers would approach some problems. So it gives you guys the idea. I won't touch upon the whole basis. That's for the mechanical material review video lecture I'm going to post and some of the advanced stuff I'm going to do after this presentation. And then, so final considerations for your CDR, what was the C stand for again? Content design report. There we go. So some considerations, some things I didn't see in their design report that I would like to see in yours, or at least not explicative in their reports that I would like to see in your guys' reports, all right? So that's essentially it. So starting off, overview of 3D bioprinter. I apologize if you guys have already seen this before. Unfortunately, somebody's asking me a question. Unfortunately, I don't think I can answer questions until the end of this presentation. I'd really apologize about that, but we'll get to you right after I'm done. Hopefully, I'm quick about this. Wow, there are a lot more questions coming in right now. Concept design. Thank you very much. So, overview of 3D printers. So essentially, well, let's just get started with this slide. Essentially, what most 3D printers and lit intake is coming up with a soft matter material, or a medium, something like a granular gel or a viscous fluid as a medium. It acts as a support for the actual soft material, whether it be another granular gel, cell tissues, HVS, HTC, but whatever we use as our primal material to make our structure. Generally, people need to have a support medium around that, so they basically use a very viscous fluid, to put it lightly. And you can see the jellyfish picture on the right over there. I don't remember which group did that. I remember Sawyer's group doing that at one point, but yeah, that's essentially how these things are tackled. Injection of substance. Okay, so that's basically the same sentence. So I think all that adds is that we basically put the nozzle inside of the medium and then they basically print out the structure. Actually, I have this video on the bottom here. It actually shows in 3D printing process happening within the medium how the trail of the substance is being left behind within the medium. You can see it's sort of similar to a wake of some sorts in fluids, how where you basically have the distribution airflow about your subject. There's some other interesting things that go into that, but there's often difficulties to define. One is that if you're 3D printing a subject, and for example, you're dragging the material onto whatever plate or whatever medium you're putting it in, dragging the material causes shear tension onto the surface. So basically, you deform your material. You actually cause that little peak spike. You know, when you guys basically go and get ice cream and you try to get the last scoop and it's always a little peak spike. That's the same thing that basically happens with the 3D printing substances. The other thing is just sulking due to gravity. Other things are environmental conditions need to be ideal. Some things, for example, some substances need to survive at 37 degrees Celsius, not a degree higher or less if it's very finicky. So yeah, so other things about 3D printers is that for these guys at least, for bioprinters, there's clearly a trade-off between quality and performance. I saw it as a consistent topic within lids. So right here we have a graph of cross-sectional area of basically the fineness of the part you're printing versus the rate that you are injecting substance into the medium and how fast you're translating the capillary tip. And you can see that there's a linear relationship. There are some that show non-linear and some that show basically non-existent patterns. But the general gist is if you have a faster rate of disposition, and let's say we keep the transition rate constant, then your cross section basically gets higher and higher. So with that interest, some people want finer quality, so we want it to be smaller, but we want to go faster. So there's a clear trade-off in performance there. And then another byproduct of physical evidence is when we're traveling through the medium, there's a wake. Because the needle is traveling through a viscous fluid, obviously. So there is an air pocket that occur at the tip of the needle. So that sort of forms a vortex-like pattern, or a vortex-like behavior onto the substance, and causes it to rift, and there will be a little distortion in your part. So that's also a finicky and very not too worrisome, but something that they've addressed in literature. Okay, so key metrics, I'm going to go through this relatively quickly. So key metrics, what I've seen that's been addressed is what's the material disposition rate. Basically, how fast do you want this thing to print? That's dependent on how much pressure you put into the into whatever your ejection system is. What will this affect? Like I've showed you earlier, it will affect your fineness probably potentially. And of course, you guys will have to do the lit review to see what other things it affects. So I won't spoil it too much. So there's also translation speed. How fast do you want the nozzle to go? Now, I think that's a customer requirement. I'm not entirely sure. Again, you guys know that better than me. But if you have to objectively meet a specific speed, how much power do you need in your motor, or whatever linear transition device you use to transfer the nozzle? So that's that's another consideration in your design. By the way, all these key metrics are quantifiable. So the number has to be put. These are basically your engineering requirements. Life cycle, fatigue, basically. How long will this thing last? Safety, which component is going to break and how will it break? That's kind of a key thing. I think you guys have already seen FMEA's failure mode and engineering analysis. And those essentially come in handy to see which component that you prioritize failing first in order to have the least disastrous outcome possible. So this is sort of on you, and you have to be very explicit in your reports about this. With that, you basically let the customer know if something goes wrong, it's not going to go terribly wrong at the very least. Okay, so with safety there, the last thing is cost, assembly time, and weight. Obviously, those take in labor, and weight obviously transportation or ease of handling. So those things also should be considered in your design reports too. You're trying to, ideally everything should be as lightweight as possible. There are some materials that need to be heavy. For example, you probably need to make the base heavy so it doesn't jumble around too much. So yeah, those are things that you have to consider in your basic design. And I think everybody has basically seen this from design one. So FMEA, if everybody just needs to familiarize themselves with how the score sheet basically looks, this is an easy Google search, so you guys can find a copy online and just use that. So crucial modules, and again, this is opinionative. This is why I found as the as constants in everybody's designs. It's obviously the nozzle or syringe, whatever you use to eject the fluid out of. The next things that come after that is the application of pressure, that basically the force that pushes the fluid out. And I've seen people use just our syringe idea, applying a pressure, and I think I've seen one person just let gravity do the work for them. So um, different ways of going about this. I think pressure is basically the way to go, but that's according to your guys' own design. So you need to translate the device. So a guide rail, a belt, or a translation, or any sort of translation device, to put that as general, is what you need. And then a frame where to hold it all, essentially. And there's also some aesthetic parts into the frame. We'll go over that in the last bit. And down there, I have a 3D printer that we have in our lab, which is called the Ultimaker. It gives you an interesting idea of how you could translate your device aside from translating the X and Y direction. You see the nozzle itself is not going down, but the platform that it's standing on is actually going up. So that actually saves a bit of room for that type of device. So you don't have to pile on a bunch of motors at the top of the platform. And it's sort of a clever way of addressing a quote unquote cheap and commercial product. So there are several 3D printers that I've seen. Several 3D printers I've seen from students in the past. I'm going to just talk about three. These are three common tackles for this problem. Actually, I think one of them is very unique. But in the general sense, everybody usually goes about this one or two ways. This one's a little bit more unique because they're using a dovetail as their transition. As I talked about guide rails, but somebody decided they wanted to use dovetails instead, which is very simplistic philosophically because you have only a small linear transition with a lesser amount of rotations needed to get to different positions. Of course, you have less transition, but you have finer control. So it was a very, very unique philosophy, and it's very easy to manufacture this in comparison to everything else I'm seeing. Unfortunately, that frame right there, which is basically the rectangular frame right here, that thing is under a lot of load because of this. And this is probably the point where I'm going to exit the PowerPoints because I don't really have any other animations after this. So I'm going to do what I was planning on doing and start doing some drawings. But yeah, this dovetail, if you can see, the primary load, probably center of gravity, is located somewhere around this area right here. With that being said, if you guys remember what shear center is, this dovetail is regardless of how fast or slow the motors move and how the module might not conduct too much torque, there is some instances of torque being influenced. And then there's some instances of a potential change in angle happening as this thing is activated. So with the kinematics involved, regardless of if this thing can handle its shear or not, which this thing was already calculated to basically be able to handle the loads that it's being applied on, kinematically wise, it won't serve as a good purpose. You want things to be stable in their designated position. If this thing is turning, you're going to be off by some positions. And if you want finer quality, that might not be the best thing to use as a support. So there's one common thing: kinematics has not been really addressed to a higher extent during these, in these past RER reports. So I highly, highly suggest everybody really nail down your mechanics and materials, and also give a reflection of how much deflection, how much twist you want in your device, because sometimes that can have a major impact on the performance. So, by the way, dovetail device, I've used this before. It's extremely heavy, and the person who made this configuration made it completely out of aluminum. And there's nothing completely wrong with that. It's very robust. It's just really heavy. And like I said, that frame is not going to be happy with the additional extra inertia it has to deal with. So there's that. The next one I want to talk about, I call this the Da Vinci 2.0 because it just looks like the device. It looks like the Da Vinci. It has a more than 6 axis. I'm going to say more than 4 axis. More than 4 axis support for printing the material. I think this is the more unique design I've seen. It's also unique because what they managed to do was they managed to quantify the volume that they're able to print in a designated space. Since this thing can't really translate left and right, this thing is subjected to a single spot, so it can only rotate. So they were able to quantify what the volume they were able to print is, and I found that as a very unique way of addressing to the customer, this is your limitations. So higher degree of precision with this kind of device, but it's much more complex. It has a higher level of complexity. You can print more complex substances with this. It's still simple in design. It's just a bunch of pistons, but cost, weight, and assembly is going to be long. Location may be difficult depending on how good you are. Now, this is completely dependent on how you good are with computer software dynamics and handling. So that's completely dependent on the person programming. I just put that there because a lot of people have that problem. Last thing is linear actuators. Linear actuator, probably the most common. That's basically what the the Ultimaker is following right now, which is a system of lead screws connect to servos that guide you to somewhat precise, not as precise as this previous device, but somewhat nice, precise locations, consistent, robust, and overall generally more accepted because of how easy it is to design or work with. So symmetry, it has great symmetry. That symmetry is absolutely fantastic for structure. Structure. If you guys are in the failures and design group, you kind of want to try and get things to be as symmetric as possible. even if sometimes the other guys don't want it to be symmetric to do something cool or fancy, structurally, it's more advantageous if it's symmetric. Ease of transition with lead screw. Yes, so lead screw design, very common. May find instability during longitudinal motion. So the reason I designated that right now is because the if you can basically see in this rotation right here, there's not much support holding it. So we have a big moment arm happening that are just dangling out on this area. If they had something like this, which is a wedge support to hold it horizontally, um, then it'll be less susceptible to possibly tipping over. But other than that, they did not include that. So there is some instability that might happen in that direction. And then the assembly time, of course. These things do take a little bit of time to develop. Not as much as Da Vinci, but still. Okay, so this is material selection. I'm just going to go over this very quickly because, of course, choosing your material is important, not only for strength and designated weight, but also what does the material properly do. And these are just materials I listed off on top of my head that perform these designated or are chosen for these reasons. So, for example, damping, general polymers. I kind of was redundant with pulling polyurethane and sorbethane, which is apparently the more popular polymer to use for damping. Um, they're redundant with single and viscoelastic polymers, and then there's silicone rubber, of course. Interesting enough, wood can also be considered a damping. It has a decent damping coefficient rate. I actually learned this from somebody who was making mountain bikes out of wood. I mean, I still haven't heard from him, but I'm assuming he's doing all right. But the wood is an interesting factor too. It also is pretty light too, and has a decent tensile strength. So that's also considered as well. Or that's something you should also consider was conductive metals, copper, aluminum, are classics. So not much to go through there. Insulation, wool is actually a pretty decent insulation material. It just gets lit on fire really easily. So keep it at low temperatures. Cellulose, that's for very specific reasons. I'm not going to get into all the materials. There's fiberglass though, specifically e-glass right here. E-glass is a type of fiberglass that's made for electrical applications. So if you're considering using some composites, and of course every unity of material, I actually specify right here, any unique material has different compositions. So there's different types of fiberglass, there's different type of aluminum, and you have to choose the one. You have to know which one is best for your application, even if you think, oh, it's just aluminum. Everything is pre-rolled, cold rolled. Everything has a different Hooke's law. Those are things you need to consider. Smooth surface, corrosion resistance, et cetera, et cetera. So you basically get the point. You need to choose a material that also fits the bill of what you're trying to tackle. I think I'm going to go a little bit faster here because right now we're going to the analysis, consideration of analysis. I kind of shoehorned this in, but this is essentially how you find the extraction or disposition fluid extraction rate. And this is a simple conservation and linear momentum problem. I didn't really put the full conservation law here. I just put the simplified form where you can just convert it into the following form. You basically find the outlet velocity of your fluid. You'll probably know most of these values. You definitely know the area, maybe the pressure, there's atmospheric pressure, but or the pressure inside the fluid. But regardless, 7 minutes left on the countdown of 30-minute count. All right, thanks for letting me know. Um, so yeah, what this section is supposed to accomplish is supposed to take you through it's supposed to take you through the engineering analysis that you guys learned from your basics, from your earlier classes that establish the fundamentals. So essentially, you guys know how to solve almost any engineering problem. It's just you have to simplify the problem into a specific or in a specific manner so that you can solve it with the tools that you're familiar with, you're available with, or you have to go look up. That's just what being part of an engineer is. You basically have to establish this learning thread. So for example, I'm doing a bolt thread here. I left this empty because I'm going to do the drawing for it. So if we have a bolt here, you know, I practiced for this and I thought my drawing was going to be good today, but seems like it's going to be a little bit finicky on slideshow. So we have a threaded bolt here. Wow, this looks just terrible. We have a threaded bolt here, right? And the general equation for a threaded bolt, if you're screwing it in, the average stress a bolt exhibits onto a thread is given by this equation right here, area of thread right here, where area of thread is an interesting function of the pitch diameter and the diameter of the bolt itself, so the inner diameter. Um, and there are lookup tables for that, essentially. You would essentially go find what your equation for AT is for your specific application, you apply it here. And if you wanted to do a failure analysis, right? For example, I know what sigma yield is, all right? We'll make sigma yield a constant. We know that. We will know AT since we'll basically measure what this and this is. So we know what the yield force is, right? So what if I decide, okay, I wanted to go ahead and thread this into an internal thread socket that's basically the same material. So this has E and this one has E. I'm just gonna say E1 because to keep things consistent. So they're just essentially the same material, same Young's modulus. Essentially, you would do something interesting, all right? You would just do a simple free body diagram where you'd say the shear that these internal threads experience is basically the circumference, right? The circumference 2 pi r, the circumference of the bolt times the length, and you can specify whatever length you want to approach, how deep you want this thing to go. That's basically what length there is, and make that equal to whatever force the bolt applies onto this. So it would be F, right? But say, for example, I wanted to know how far I wanted to go in where this thing causes failure on the system or on the internal threads. Well, I could just rearrange this equation to see how far this thing needs to go in by finding L, and it eventually just becomes this, where I would use Fy here, and then everything on the below side is, of course, shear. And assuming you know what the yield shear is for this material, essentially it's the same thing as yield here. So I guess I'm going to go ahead and replace this with home draw this. And then 2 pi r. What you'll essentially find here is that you'll find that the depths, the length depth that you usually get for this equation is usually just 2 threads, which is interesting because the rule of thumb is 5 threads. But most rule of thumbs are just double what the actual safety factor or norm is. So that's a very interesting fact. If you do that analysis, you'll find that to be true for most cases. So that's for bolt thread analysis. So structural assumptions in geometry. So again, you're engineers, you have to make assumptions to simplify the problem for yourselves. For example, if I want to do something like a plane stress problem, right? I'm sorry, a plane strain problem first. So with a plane strain problem, I'm assuming that the width or thickness of the substance is so long. I meant to say plane strain. The thickness of the substance is so long that it doesn't really matter how much it elongates. It's indefinitely long. So we won't get an accurate, or we won't get a reasonable or relevant non-abstract answer there. So we assume plane strain where we say, okay, let's just make the strain in the thickness direction 0. So that simplifies some of your equation. For example, that basically makes EZ go to 0, which is huge. That simplifies a lot of things. And then all the X and ZY also goes to 0. I'm assuming, oh, 2 minutes, good, good. I actually wanted to go to 40 minutes, so this is actually great for me. So that's plane strain. Another simplification is a plane stress, where you assume that that whatever substance you're dealing with is not that thick. It's actually very thin. So stress does, stress doesn't matter matter in this direction because there's really no material. If any out of plane force is applied to this thing, it'll basically break. I kind of made this thing just look like a sausage, whatever. So essentially what you could do is you could say, you can essentially make your out of plane stress equal to 0. And due to Hooke's law, you can basically make tau xz equal tau zy equal 0. Okay, so these are simplifications that will make your life analysis much easier. For geometric considerations, all I meant to say here is, for example, if you're working with an I-beam, why would you choose an I-beam over a regular rectangular beam, right? Well, it's obvious because I-beams, I think you guys already seen this hundreds of times, I-beams basically are built for bending. So for bending, the max stress happens at the surface tips or the tops right here. So really the web doesn't really do much, which is why for I-beam considerations, a lot of people, and let's just imagine this part right here, the web of the I-beam, would put holes here to simplify or lose weight. Some people say reduce cost, but doing the labor to drill the holes is already more than enough to compensate for that. So, so these are geometric considerations that you have to consider as well. Why would you choose an I-beam? Why would you choose a C-beam? Why would you choose this or that for your parts? And this goes in tow with how you calculate these problems. So keep that in mind when you do your designs. Another thing aside from plane stresses, plane stress and strain is axis symmetric, and I'm going to do a basic O-ring example. Hopefully this helps you guys with your syringe problem. The Hooke's law equation for an O-ring, and I'm going to do things in polar coordinates, by the way. So this is in the radius direction. This is in the tangential direction of the polar coordinate. Okay, I'm kind of doing things out of order here, but here's out of plane, and then tau RZ. By the way, if you're working on failures, you probably might want to write this down because this equation will become really useful when you guys do your analysis for the syringe barrel and whatever O-ring or gasket you're dealing with. This is the Poisson ratio. This is the stiffness modulus, and I'm assuming everything's isotropic. And then the rest of the stiffness equation is this, 0. Okay, and then yeah. Oops, 1 minus v here. Whoops, gotta make that look better after this. V here, and I mean new. Whoops, I didn't mean to say new. I meant to say okay, I guess I can erase this while I'm at it. New here, everything else being 0. This right here would become 1/2 minus new. Okay, and then your strains, which is epsilon RR, epsilon theta, epsilon epsilon ZZ, and then last but not least tau, gamma RZ. Let's just make that better. Okay, so with this, you essentially have your constitutive equation for axis symmetric. Now, for an O-ring, right? Let's assume, for example, so we're doing axis symmetric. So assuming this is this axis symmetry, here is whatever gasket you're applying. Here's whatever wall the gasket needs to hit, right? Assume that this side of the gasket is fixed. Assume the bottom half of the gasket is fixed, right? It needs to travel some distance. We're going to say delta here, and you're applying a force or you're applying a pressure, right? So with that, what this basically says, and you apply it to the top above equation here. So if this direction right here is the radial direction, we know what ER is, or epsilon R. Epsilon R is essentially whatever the length of this radius is, or whatever the length of this section here. I'm going to call it, I'm not going to call it dx. We'll call it L though. So assume the length is L here. Apologize if this looks awful. I'll try to clean it up before I post this. That's basically your epsilon R. I'm going to assume that epsilon theta are 0. I'm going to assume that it does not expand in the or if you look at a point and we compress the O-ring, it does not expand in the tangential direction, or it doesn't move in the tangential direction. So I'm going to assume this 0. Again, if your boss doesn't want you to make that assumption, then you basically go back and you fix it and you use compatibility equations along with this, but I'm going to assume this for now until given notice that it's not allowed. Obviously, we're moving down, so epsilon ZZ exists, and I'm going to assume that in the polar coordinates, there is no change in angle, so I'm also going to assume epsilon RZ is 0. Epsilon RZ is gone, so basically, if you look at this equation, it affects tau RZ and makes that 0 right there. Obviously, we've got sigma ZZ. We obviously have a sigma theta theta right here. And we're going to compress against this wall as soon as we expand a specific amount. And we already know what sigma ZZ is. ZZ is essentially P, whatever pressure I applied. So, right, so with that given, we know what this is, and we know what this is, okay? So yeah, let's see now. You have 3 equations. You have 3 unknowns, essentially, this, and this. And you basically go ahead and solve for whatever your stress is in the sigma r and sigma theta, and then you can transform that into the XY coordinates. So this is one way to simplify such a 3-dimensional problem into 2D, and you can also do that with finite element analysis as well. But I think I've stressed, or I've gone over that enough. So stress concentration, I just want to talk about this briefly. Stress concentration is something you should consider when you, for example, if we're going to look at a simple cantilever beam, and it's undergoing a, we're going to do a shear moment diagram here. This is for shear, and this right here is for moment. And obviously, if we're going to follow our right-hand rule here, I'm going to assume that the z-axis is going out of plane. Okay. So shear is going down, doing something like this. Okay. As a result, moment is going to be, oh, sorry, the z is supposed to be positive. It works a lot better if it's positive. Okay, so z is supposed to be positive, so the moment diagram would look something like this. Okay, so essentially, the whole point of stress concentration here is if you have, for example, a fillet right here, right? You might want to emphasize, because the maximum stress occurs right at this base right here. If the maximum stress occurs here and you have a fillet, this is a source of stress concentration, KT sigma max. And if you guys still have your Shigley's books, or there's another book called Peterson's stress concentration factor manual, basically you'll be able to get experimental data on what this quantifiable KT is, multiply whatever your stress is, your bending stress is at the base, and you'll get your stress, your considered stress concentration, maximum stress, which is very important because, again, some stress concentrations can be marginally higher than what the maximum stress without it is. So that's something you need to also look into your design. So I'm just going to briefly touch upon this using finite element analysis. Using finite element analysis, of course, it's a bunch of pretty colors, but it is a system of equations, and I will have a video that posts this later that discuss what the theoretical equations look like and what the software actually does instead of just make things look nice. But essentially, you heard this plenty of times, garbage in, garbage out. So you need to verify, you need to start with a simple problem first, and you need to verify whether your model is correct or not, which is what a lot of people in these concept design reports do. They take a problem they simplify it into a 2D case, and they make sure that there's stress that they find at a specific location and their displacements are exactly the same, which means you're doing your model correctly. And if you're doing your model correctly, and you know you're doing it correctly because you're matching with your theoretical equations, then what that essentially means, I mean, your analytical equations, what essentially that means is you have a valid model to work with. And obviously, a lot of people also do that, experiment with more complex models. But yeah, in finite element analysis, what you'll essentially do, for example, if I have a plate with multiple holes like this, right, something complex, you would not analyze this first. You would try to start off with something simple, a plate with a singular hole in it. You would analyze this, see if your analytical correction or your analytical solutions match whatever stress concentrations you find around here or here. Okay, if you find that your stress concentrations at these points match your finite element analysis, then you're doing it correctly. Then you can start transitioning to doing more complex shapes. Because now that you know the model is valid, you can basically start adding in more and more complexity because you know your fidelity is high. So that's essentially how you tackle finite element analysis. And one more thing is I saw somebody do a finite element analysis of a bolt with their threads still on. Unless you're trying to do a specific, and they were trying to do a shear test. Unless you're looking specifically for a stress concentration at these hinged points here, there's no reason for you to model something with complex geometry. If you're just doing a basic shear, you can model it as just a nominal diameter. And I am drawing things poorly today. And simplify the geometry. This will simplify your calculations, and you'll find that your answers, if it's not too effective of your geometry, won't be completely off. So that's something you have to consider when you're using finite element analysis. Simplification of geometry, not necessarily a bad thing. Another thing about simplification of geometry is if you have symmetry. Let's take, for example, I have this truss structure here, and this is supposed to be a symmetric truss structure. I apply a force P here, and let's just say it's a simple support, right? So if I have something like this, I would not want to go ahead and just model the entire thing, right? Just like the O-ring example here, I don't want to go ahead and model the entire O-ring itself. I've simplified it to a 2D problem to make calculations easier. You would do the same thing with finite element analysis. You'll find that your results for the full model and simplified assumption is going to be essentially the same. So I would probably simplify it to say it would look something like this, right? P over 2, and obviously everything has a reaction here, and then whatever truss structure reaction is here, and obviously our reaction from the supports. But yeah, you would simplify it to a easier model for you to do the analysis, as long as you keep your boundary conditions consistent with the full model. So that's something you also need to take into account for when you do finite element analysis. So that pretty much ends this presentation. So the overall considerations you need to do for a concept design report, that, and some that I did not see when I was looking at the prior reports, is to make sure you show all of your work. Make sure you give all your approximations, assumptions, and solutions, because a lot of people might be looking for that if they're going to break off of your design. They want to know what your logic is. So you need to make sure your CDR reflects that. Kinematics, a lot of people forgot to calculate how much a part will twist or bend, and that's extremely important. If a part should not interact with another part, if it bends too much, you need to make that clear. That's part of the concept. That's part of the concept design. Of course, be explicit why you chose a material, why you chose a tolerance, why you chose a safety factor, etc. Make sure you have integration diagrams and sub-assembly. Everything needs that. Every single part you put in, every screw needs their own dimensions, their own plots, etc. These need to be well documented for future use. So that's something that is highly critical in industry. If you miss that, you're going to be pissing off a lot of people in the later future. But yeah, those are things you need to consider. And don't forget your logistics, like assembly time, cost, weight distribution, something that your customer will want to see. So yeah, with that, that's basically the whole gist of how you would go about designing a 3D printer with some extra analysis in between. And I just want to check up on time right now. Dr. Trump, how much time do we have left? Okay, 15 minutes. Okay, so with only 15 minutes, I don't think I'm going to be able to cover one of the subjects you guys have been highly requesting, which is plate theory. I think I'm going to have to do plate theory in a separate video. But for now, I'm going to go ahead and show you how you would calculate the stress concentration for a hole, or a hole inside we'll consider a half plane. I'll show you that in this analysis, the depth of the plane becomes arbitrary. So, Dr. Trot, I'm going to go ahead and stop sharing my screen for a second so I can set up for that. I'm just going to open up a new PowerPoint so I can draw in. So give me 1 second. And if you want to speak, go right ahead.
Oh, well, I was going to say, well, Brandon is setting up for the next derivation. Does anybody, and we'll have to have Brandon multitask a bit then, does anybody have any questions on his presentation up until now? Seems like we're okay. All right. So just as a,
Okay.
oh, good. Okay. Someone give a thumbs up. Awesome. Thank you. So just as a follow-up, I was in the background while Brandon was presenting, sending out tracking numbers as well for the 20 or so of you that didn't get the RER kit tracking numbers yesterday. So I think I've got like 3 more to go, but by the end of the session today, everybody should have their kit tracking number. And I looked at a couple of them, and they're already, as of this morning, have left Jacksonville, which is the main USPS facility in the region, off to all their various their destinations. So hopefully, maybe with the exception of Brandon, who is 6 days away by mail, they should get yours the next day or two.
Yep. Hopefully those kids don't get eaten by the deers outside right now. They're kind of messing with my yard. I'm gonna scare them off after this. If somebody wants proof, I'll take a picture of it. But yeah, let's just go ahead and continue. So this next thing I'm also gonna post this up online too, is this is what we call hole in a plate half plane analysis. So I'm gonna go ahead and share my screen again. Share. Okay, so hole in a plate half plane analysis. This is probably what you'll use for validating your hole in a plate problems, or hole in whatever structure you're dealing with, as long as we consider it, and this is key, as long as we consider the structure a half plane. So half plane assumption. Half plane, if people want to know, is just an arbitrary block with an arbitrary thickness. So we have a lot of derivations that become that become convenient due to this assumption. And we're going to go ahead and throw a hole in there. Okay, there's a hole. We're going to go ahead and establish our coordinate systems. Always establish a coordinate system when you're doing a structural analysis. If I don't see that in your reports, I will definitely take points off. Okay, so we have a half plane, we have a hole here. So let's assume on this half plane that we're just applying a uniaxial load, sigma, we're going to call it sigma 0, okay? And obviously there needs to be equivalent on the back, or else there won't be stress in the system, okay? So we're applying a uniaxial load, and we're going to use what is basically known as Airy's stress function. Airy's stress function, Airy's stress functions are clever little mathematical devices used to first assume the solution of the function and then prove it kinematically later. So what I'm not going to do is do the derivations for it. What I'm instead going to do is just tell you the answers directly in polar coordinates. Again, we'll do things in polar coordinates because it's a radial circle. You can always just convert it back to XY coordinates afterwards. So we'll start off with sigma r, which is 1/2. I'm going to be very complete here since I think I have time. Sigma r, whatever the applied uniaxial stress is, 1 minus a squared times the radius of that circle. So what is a? A is essentially from the origin or center of that circle to whatever radial distance you choose, okay? So r is the radius of the circle, but a is whatever radial distance you choose, as long as it's not less than r, okay? Let me put this here. A must be greater or equal to r. Otherwise, you're just analyzing empty space, and that leads to absolutely nothing. It gives you negative for a positive stress. So that's basically a no-go. Plus, my bad. I need to put a bracket here. Okay. Plus 3a 4. Of course, people should, if you're in the structural team, you should probably write this down. Minus 4a squared r squared, close parentheses, and with that multiplied by cosine 2 theta, and then end the bracket. Right now the deers are trampling over my flowers. I'm slightly getting agitated. So for stress in the tangential direction, it would be as follows. 1 minus a squared r squared minus 1 plus 3a 4. This is a 4. I'll write these equations out using insert and equation solver. You guys won't have to bear with dealing with my scribble here. Cosine 2 theta. I personally like to write things out first so the class can follow, then afterwards post neat solutions because you've already seen the derivations once. And this right here becomes arbitrary, and I will show you why in a second. I'm just going to write it relatively fast. Power of 4 plus squared sine, okay, sine theta. Okay. For better or worse, those are your equations. Those are area stress functions to solve this problem. So what happens if I decide to make A equal R, right? If I make A equal R, what essentially happens is your radial stresses and your shear stresses go to 0. The only thing that is left is your tangential. And this is proven, actually this is proven in experiments. There's only tangential stresses happening around the hole rather than radial. And that makes sense because if anything's radial past the or less than the hole diameter, it equals no stress. So that's why tangential conservation. There's also some conservation of momentum happening in structures too. So that's kept consistent. This one basically equals sigma 0, 1 minus 2 cosine 2 theta here. We're just about to get done. Okay, so now that we know this, right, I'm going to go ahead and show you a few case examples here. Let's look at one case example. Case 1 is if I have a sigma 0 equal to sigma x. So basically, what I just did earlier, sigma 0. So any radial direction you choose, because we have a theta term in this, 1 minus 2 cosine, and it's the same equation. You just basically choose what your theta term is, and you solve the problem that way, and you basically get your theta stress in the tangential direction, and you can convert that to XY again. Case 2 is much more interesting because what happens if I decide to apply it in the Y direction instead of the X direction this time? So sigma 0 equals sigma Y. Okay, so what essentially happens is if I draw the same system again, essentially I can do, and let me just be complete here for God's sake, completeness sakes. You could think of it like a transformation of the XY, flipping it so that we have this X prime direction here, we have this Y prime direction here, and then we're choosing some theta prime tangential direction to analyze from the new coordinate systems here. And you can barely see that right now. But essentially what you do is you take this equation, but instead of theta here, 1 minus 2 cosine 2 theta prime. You'll have theta prime. And what theta prime is essentially a rotation from your original coordinate system to this. So basically you're rotating the stress from here to here. And the logic behind that is if you take this new theta prime here plus pi over 2, which is how much we had to transform it, you'll get what we need to apply originally in the original equation here, but instead we need to deal with theta prime, so we move the pi over 2 the other direction. So theta prime now equals theta minus, oh, sorry. God, one of these days I need to get a doc cam like Dr. Tran, so things would not look so horrendous. Pi over 2, okay? And essentially that's how you would solve this equation right here if you only have a case where you have sigma y. Okay, I will go ahead and fix that in post. See, case 3, I think this is probably this is second to last case. Case 3 is what happens if you have sigma 0 equal, you have a sigma x and you have a sigma y, basically. You have a bidirectional application, and these can be, these don't need to be the same. In this case, we'll make it the same, but sigma y can be like twice the size of, or twice the amplitude of x. Essentially what you do is you do something, you do basically superposition. You would solve for sigma x first if you were to only have a sigma x first. Then you would add that if you were to solve it only if there was a sigma y. So it's a method of superposition you apply into stresses. And essentially that's really all you need to do in terms of solving for holes, plate hole theories and stress concentrations due to that. There's just one more thing, which is case 4. If you have shear. In shear, what essentially happens is you consider that theta prime. You consider it, if you remember more circle, shear happens 45 degrees between two principal axes. So you'll just take theta minus 45 degrees, which is pi over 4, and that's essentially it. And you would apply it back to this equation right here. Okay? I mean, sorry, not that equation. This equation right here. Okay? So, yeah, with that being said, that's really all I need to cover for now for advanced topics of materials. So hopefully that lets you guys can play around with that, and if you guys have hole designs, you can use this to your advantage and basically see if your structures fails. Okay, so that's essentially it, and I'm pretty much done. So
Yay!
all right, hey, you got the floor again, Dr. Tran.
We made it. Okay. Anybody have any questions for Brandon? Nope. Seems like everyone's okay. All right. We're getting some accolades. Cool. Well, let me. I'm gonna stop recording.